In this video, I want to look at three examples of transformations from the z-plane to the w-plane. The first one, we have the circle mod z is 3 being transformed by w equals z minus 1 over z plus 3. We are starting in the z-plane and finishing in the w-plane. A good general rule when going from z to w is first to find z in terms of w. We've got that w is z minus 1 over z plus 3. Multiply both sides by z plus 3. And a little bit of algebra gives us that z is 3w plus 1 over 1 minus w. We are looking for the image of mod z equals 3. Well, z is 3w plus 1 divided by 1 minus w. Mod z is 3 gives us that as an equation for w. This now is the image of mod z equals 3 in the w plane. We can multiply both sides by mod 1 minus w. And I can take a factor of 3 out from the left-hand side. Divide both sides by 3, and I get mod w plus a third is mod, well, the modulus of 1 minus w is the same as the modulus of w minus 1. This should be familiar. This is now the perpendicular bisector of the line joining the points minus 1 over 3, 0, and 1, 0. And this is u equals, midway between minus a third and 1 is u equals a third. We must use u and v because we're in the w plane. And there we have a picture of this transformation. We start with mod z equals 3, and we finish with u equals a third. The second transformation looks very similar to the first one. Find the image of the circle mod z is 4 under the transformation w equals z plus 4 over z plus 2. We are going to find that it does turn a different direction when we get going. We are still going from z to w, so it's still best to find z in terms of w as the first thing. So let's do that. Well, I've done this for you. Let's just follow it through. We multiply up by z plus 2. We find z. And we're looking for the image of mod z is 4. The image of mod z is 4 is going to be mod 2w minus 4 over 1 minus w is 4. This looks very much like the example before, so let's carry on the same sort of way. Mod 2w minus 4 is mod 4 times mod 1 minus w. Take the 2 out and cancel, and I'm left with mod w minus 2 is 2 times mod w minus 1. So this is no longer an easy straight line. What we have now is Apollonius's circle. And the only way to deal with Apollonius's circle, or I think the best way, is to rewrite w as u plus iv. And continue from there. Well, I've done this for you, and you can see that putting in the u and the v, we get squaring both sides, u minus 2 squared plus v squared, square the 4, easy to forget to do that, u minus 1 squared plus v squared, little bit of simple algebra, down to there, complete the square, add 2/3 squared each side, and there we have the equation of a circle, center 2/3 naught, and radius 2/3. You can always stop the video and look at it longer if you wish, or of course it will be in the notes. And so here we have started in the z-plane with mod z equals 4, and we finished in the w-plane with a circle, center 2/3, radius 2/3. In the third example, we're going to look at the image of y equals 2x under the transformation w equals z over z plus I. This already looks different. The image of y equals 2x is not the sort of curve we've been thinking of in previous examples. We're still going from the z-plane to the w-plane, so as a general rule, it's still a good idea to find z in terms of w. So let's do that. We have that w is equal to z over z plus I. Multiplying both sides by z plus I, wz plus wi is equal to z. And this gives us that z is equal to iw over 1 minus w. Finding the image of y equals 2x doesn't have the same sort of modulus feel to it that we had in the previous two examples. The technique here is to write z is x plus iy and w is u plus iv. We know that x is the real part of z and that y is the imaginary part, so what we need to do now is to sort out the real and imaginary parts of iw over 1 minus w. That we're going to do down the bottom here. Let's just have a look at that. We have now z is iw over 1 minus w. Z is x plus iy. W is u plus iv, u plus iv. Simplifying that, we get x plus iy is iu minus v over 1 minus u minus iv. Well, we want to extract x and y. X is the real part, y is the imaginary part. So how can we do that? We multiply top and bottom by the complex conjugate. That's 1 minus u plus iv over 1 minus u plus iv. If we do that, we shall be able to extract the real and complex parts easily. And this equals iu times 1 minus u minus uv minus v times 1 minus u minus iv squared, all divided by 1 minus u squared minus I squared, that's plus v squared. So what we're looking for now, we're looking for the image of y equals 2x. In other words, we want the imaginary part to be equal to 2 times the real part. And this gives us imaginary part u 1 minus u minus v squared over 1 minus u squared plus v squared, is twice the real part, twice minus uv minus v minus u, also over 1 minus u squared plus v squared. So I've not bothered to put the denominator in because it cancels. Now a simple piece of algebra should take us to the equation. And simplifying this, we get u minus u squared minus v squared minus uv plus uv disappears. That leaves me just with minus 2v. Sorting that out, we get u squared minus u plus v squared minus 2v is 0. Complete the square, add a half squared. Complete the square, add 1 squared is a quarter plus 1 is 5 over 4. There's the completion of the square. That gives us a circle, center, half 1, and radius 5 over 2. So in this case, we started with the line y equals 2x, and we have finished with a circle, center, a half 1, and radius root 5 over 2. So those are 3 examples of finding transformations of images in the z-plane to the w-plane. It's a good technique. You might well find some examples where you can do something by a slightly shorter method, but what I've done here will take you through all of the examples that you're likely to meet.